All right, for homework number 33, we are practicing our inverse trig antiderivatives. So you want to recognize, remember, it's arctan and arcsine that are the most common. So I have 7 over 16 plus x squared. So anytime I see a sum of squares in the denominator and just a constant in the top, that's your hint that this is going to be arctan. So a is the square root of 16, u is the square root of x squared, du dx would just be 1, or du is equal to dx. So I think it's a good idea to set this up before you actually get down to the integral so you don't miss anything. So there's this constant of 7, which I'm going to pull out in front. I have 1 over a squared plus u squared, and dx is just du. All right, so there's a 7 out in front. The antiderivative of this is 1 over a, so 1 over 4, times arctan of u over a plus c. So, and instead of u over a, we could probably just write x over 4. So 7/4 arctan of x over 4 plus c. For the next one, it's the square root of a difference of squares where the constant is first. So that's arcsine. So a is equal to the square root of 1. U is equal to the square root of x plus 1 squared. Du dx would still be 1. So when we rewrite this integral, there's a 1 on top. This is the square root of a squared minus u squared, and dx is just equal to du. This does not have a 1 over a in front, so this is just arc sine of u over a, so x plus 1 over 1 plus c. So we're just kind of practicing recognizing the two main formulas here. All right, this one is another difference of squares here. What's this extra t doing up here? It's because this isn't just 1 minus t squared. So let's take a look at this. I think it's arcsine, so I'm going to say, okay, then a would be 1. Now u squared would equal t to the 4th, so u would equal t squared. So du dt would be 2t. So that's what this 2 is doing up here. And remember, you can solve this for dt to do your substitution. Or you can say, I have a t dt. I would like this to be 2t, and I can accomplish that so that this is du. I can accomplish that as long as I balance it out with a 1/2 in front. So either way, you're going to get a 1/2 constant that you pull out, and then this is 1 over the square root of a squared minus u squared, and this 2t dt is my du. So 1/2, arcsine doesn't have a 1 over a, so 1/2 arcsine of u over a, so u is t squared over 1 plus c. For the next one, again, it's like, what is this x doing down here? But just go with which one you think it is. I think I see square root of a difference of squares, so I think it's arcsine, so set it up. A would be 1. U would be ln x, because that's the quantity that's squared. Du dx is 1 over x. So that's why there's a 1 over x there, because du is equal to 1 over x dx. So you have 1 over x dx, so that's du. No extra adjustments to make. We have the integral of 1 over the square root of a squared minus u squared du. So that is arc sine of u over a, so natural log x, over 1, plus c. Sometimes this looks weird when e is involved, but for this one, I see a sum of two squares here, and u sub isn't going to work if I let the denominator equal u, because du would be e to the 4x, involve in e to the 4x. I don't have that. So this again is a would be square root of 4, which is 2. U squared is e to the 4x, so square root that. E is e to the 2x, so that's where that's coming into play. Du dx would be e to the 2x times 2. So du is equal to 2e to the 2x dx. You have e to the 2x dx. You need a 2 in there to make that du. And you're going to balance that out by putting a 1/2 in front. So you have 1/2 integral of 1 over a squared plus u squared du. That's 1/2 times 1 over a times arctan of u over a, e to the 2x over 2, plus c. I'm not taking the time to rewrite. Obviously, this is 1/4 out in front. All right, now what about 21? I could look at this. I could try this with arctan, but it's not arctan because even though I can make this 1 plus x squared, if a is 1 and u is just x, then that's not going to get rid of this. So just because you see a sum or a difference of squares in a denominator, don't forget about all of the other methods we've learned. So what about u sub? Let's try u sub. U would equal the denominator, x squared plus 1. Du dx would equal 2x. Now you have an x minus 3 here. If it was just the x, then we'd be good. So here's what we need to do on this one. We need to split this up. We need to split it into two integrals, x over x squared plus 1 dx minus 3 times the integral of 1 over x squared plus 1 dx. Excuse me, I'm separating them because u sub works for my first integral. I just need to make some adjustments here. I need to put in a 2x dx to get my du and balance that with a 1/2. So the first integral is 1/2 times the integral of 1 over u du. That's done. Now this one is arctan because u is x, a is 1, du dx is 1. So this is minus 3 times the integral of 1 over a squared plus u squared du. Now my u's are different things. I don't know if I would really need to make one a w or something like that. I'm not going to worry too much about that. But this would be 1/2 times the integral of 1 over u is ln, absolute value of x squared plus 1. Although that's always positive, so it probably doesn't need an absolute value. Minus 3 times, this is arctangent, so 1 over a would be 1 over 1. Arctangent of u over a, x over 1, just x, plus c. So that's a tricky one. U sub doesn't take care of the minus 3 on its own, so you've got to split it up and then go from there. Right, evaluate the integral. So now we're just doing definite integrals with our inverse trig. So this looks like arc sine to me. So a would be 1, u would be 3x, du dx would be 3. And in other words, that's du equals 3 dx. So we have 3 dx, that's du. All right, so this is now the integral from 0 to 1/6. I'm not going to change my bounds, of just 1 over square root of a squared minus u squared du. And that's equal to the arc sine of u over a, 3x over 1, evaluated from 0 to 1/6. That's equal to the arc sine of 3 times 1/6 is 1/2 minus the arc sine of 3 times 0 is 0. Arc sine of 1/2 means what angle between negative pi over 2 and positive pi over 2 makes sine equal to 1/2. That's pi over 6. And then arc sine of 0 is 0 because sine of 0 equals 0. So our answer is just pi over 6. Okay, for this one, a would be 1. U would equal sine x. Du dx would equal cosine x. Cosine x dx we have, so that's du. So this is the integral from 0 to pi over 2 of 1 over a squared plus u squared du. That's equal to 1 over a, so 1 over 1, arctan of u over a, sine x over 1, evaluated from 0 to pi over 2. So this is the arctangent of sine of pi over 2. Sine of pi over 2 is 1. Minus the arctangent of sine of 0 is 0. Now, arctangent of 1, what angle makes tangent equal to 1? That's pi over 4. What angle makes tangent equal to 0? 0. So solution is pi over 4. For the next part, we kind of did this in our notes. Determine which of the integrals can be found using basic integration formulas you have studied. So this first one is arcsine. So yes, we can find this. It's equal to arcsine. I'm not sure what work I wrote in my original one, but it's equal to arcsine of x plus c. This one is not equal to arcsine, but I believe we did this in the notes. U sub will take care of this one, right? Because u would equal 1 minus x squared. Du would equal negative 2x dx. So we could take care of that. So yeah, we can make this negative 1/2 times the integral of 1 over square root of u du, and we could solve that. I guess we might as well take care of it, huh? So this is u to the negative 1/2. Add 1 to that, you get u to the 1/2 divided by 1/2 plus c. All right, and then this last one. Now, if you look back to your notes, this would be arcsecant, 1 over a arcsecant, if it was x square root of x squared minus 1 on the bottom. And we can't just factor out a negative 1 because square root of a negative is not going to work for us. So this one we can't do. All right, last two problems. Find the area of the region. So it's hard to see, but the little pink shaded region here is between 0 and 1. So we want to find the integral from 0 to 1 of, let's put the 2 out in front, 1 over square root of 4 minus x squared dx. A would be 2, u would be x, du dx would be 1. So this is 2 times the integral from 0 to 1 of 1 over square root of a squared minus u squared du. That's equal to 2 times arcsine of u over a, x over 2, from 0 to 1. Remember, arcsine doesn't have a 1 over a in front of it. So this is 2 times the arcsine of 1/2 minus the arcsine of 0. That's 2 times arcsine of 1/2 is pi over 6. Arcsine of 0 is 0. 2 times pi over 6 is pi over 3. And our second to last problem here. Again, hard to see the shaded region, but it was between 1 and 3. So now we want the integral from 1 to 3 of, this one's kind of tricky. I remember this now. What's the deal here? U sub's not going to work, and I can't factor this right now, and it's not set up like inverse trig. So what do we do here? This is a throwback to complete the square, which we have not emphasized in our pre-calc class. We don't use it very much. It's pretty rare to see it here. But if I could make this a complete the square problem, it would give me something squared, a constant plus something squared, and so then I'll be able to make this arctan. Okay, so let's remember complete the square. It's x squared minus 2x. You divide negative 2 by 2. It's negative 1. And then you square that, positive 1. So you add that value here. That's going to be a perfect square. The plus 5 hangs out on the outside. And because you just added 1 to the denominator, you need to turn around and subtract 1 to keep things, mathematically the same as the original problem. Okay, so then what does that do for me? Let's make it look more like arctan. 5 minus 1 is 4, and then we would be adding this perfect square trinomial, meaning this factors into x minus 1 squared. And now it's an arctan. So a is 2, u is x minus 1, du dx is 1, so du is dx. So now it's the integral from 1 to 3 of 1 over a squared plus u squared du. And that is equal to 1 over a arctan of u over a, x minus 1 over 2. And we're evaluating that from 1 to 3. So 1/2 arctan of 3 minus 1, 2 over 2, 1, minus 1/2 arctan of 1 minus 1 is 0 over 2. This is 1/2 times arctan of 1 is pi over 4, minus 1/2 times 0. Half of pi over 4 is pi over 8. All right, that's pretty tricky. Am I going to put complete the square on my test? No, but that's not to say that it definitely won't be on the AP test. Maybe they throw one of these at us, so good to have seen it. All right, let's see. This area, it's hard to see. They have labeled it for us. They want us to stop at x equals ln radical 3. So we want the integral from 0 to ln radical 3 of, let's pull the 4 out here, e to the x over 1 plus e to the 2x dx. So we saw something similar to this in a previous problem, but now it's just e to the 2x instead of e to the 4x on the bottom. So a is 1. Oops, not e. U squared is e to the 2x, so u is just e to the x. And du dx is also just e to the x. So we have du, no extra adjustment needs to be made. So this is 4 times the integral of 1 over a squared plus u squared du. We're going from 0 to ln radical 3. So 4 times 1 over a, arctan of u over a, evaluated from 0 to ln radical 3. Arctangent of e to the natural log of radical 3. This is a log exponential property. The base e and the natural log cancel each other out. They're inverse operations, and you're left with radical 3. And then e to the 0 is 1. All right, so what angle makes tangent equal to radical 3? If you need to give yourself a little unit circle here, at pi over 6, we are here. At pi over 3, we are here. And tangent is y over x, so it's at pi over 3. We should know arctangent of 1 is pi over 4. That's because here it's radical 2 over 2, radical 2 over 2, at pi over 4. And then, okay, what is this? Let's see. These could be over 12, right? So 4 pi minus 3 pi. 1 pi over 12 times 4 is pi over 3. All right, so that finishes this homework. Please come into office hours if you have questions on anything in this assignment.